This is Catherine Schmer at Chattanooga State Community College. This is video 1 of the section on planes in space, and in this video we will be discussing how to write the equation of a plane. Let's start by thinking about what determines a plane. So common answers to this are 3 points, or 2 intersecting lines, or a point and some kind of tilt fixing the way that your plane is tilting in space. So if I look at this picture, I can have the point P naught being x naught, y naught, z naught, and then some vector that's normal to the plane. So I'm going to call that vector n, and it's 90 degrees no matter where I am on the plane. That vector, that normal vector, will actually fix the tilt of my plane in space, and so the tilt is given by a vector normal to the plane. Now these two pieces of information allow us to develop the equation for a plane. A plane through the point P naught, x naught, y naught, z naught, normal to n equals ai plus bj plus ck has component equation a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Now it's very important to remember to put that equals 0, otherwise you're not giving the equation for a plane, you're just giving an expression. Also notice that the a, b, and c, so those components of the normal vector, get written in front of your parentheses around x minus x naught, y minus y naught, and z minus z naught. Example 1 asks us to find the equation of the plane through the points P naught, 0, negative 2, 4, Q naught, 3, negative 1, 1, and R naught, 5, 5, 6. We need a vector normal to the plane. Remember that normal vector is going to fix the tilt of our plane. So what we want to think about is how we would get that from 3 points. Well, we know that since P naught, Q naught, and vector P naught, R naught are both in the plane, their cross product will be perpendicular to the plane. Remember that the cross product is always 90 degrees to both of the vectors that you're crossing. So I'm going to start by actually finding vectors P naught, Q naught, and P naught, R naught. So P naught, Q naught is equal to the components of Q minus the components of P. So I get 3 minus 0, negative 1 minus negative 2, and 1 minus 4. So this gives me the vector P naught, Q naught equals 3, 1, negative 3. I'll do the same thing for P naught, R naught. So I have 5 minus 0, 5 minus negative 2, and 6 minus 4, giving me the vector P naught, R naught equals 5, 7, 2. Now remember, I have to take the cross product to get a normal vector to the plane. So n equals the cross product of vector P naught, Q naught, and P naught, R naught. So I put it in my 3 by 3 matrix, I, J, K on the top row, 3, 1, negative 3 on the second row, and 5, 7, 2 on the third row. So my I component is going to be multiplied by the parentheses 2 plus 21. And remember, my signs alternate, plus, minus, plus, so I have minus j times 6 plus 15, plus k times 21 minus 5. If you need a refresher on taking the cross product, please go back to the video on cross product. So this is equal to 23i minus 21j plus 16k. So there's my normal vector to the plane. So that's what I'm going to use for my my A, B, and C in the equation for the plane. So next, I can use any of the 3 points on the plane for x naught, y naught, z naught. So I know that I need some point on the plane and a normal vector to the plane to make my equation. So I'm going to go ahead and pick p naught. So I'm going to use the point 0, -2, 4. So now my equation of the plane is 23, that comes from the I component of the normal vector, times x minus x naught, so x minus 0, minus 21, the j component of the normal vector, times y minus -2, so the -2 comes from the point p naught, plus 16, so the k component of my normal vector, times z minus 4, so z minus z naught. And then remember, it's important I include equals 0, otherwise I'm not actually giving the equation of the plane, I'm just giving an expression. So now if I wanted to simplify this, I would distribute my 23, distribute my minus 21, and distribute my 16, and then gather any like terms. So I get 23x minus 21y plus 16z equals 106. So at that point, it's just distribution and rearranging which side your constants are on. So that's how you find the equation of a plane in 3 dimensions. You get your normal vector, you find a point on the plane, and then you just plug it into the formula and then simplify. The way you can check is you can check that P naught, Q naught, and R naught each satisfy the equation. So all 3 points on your plane should satisfy the equation for the plane that you found. So if you want to go ahead and check that, that will tell you whether or not you got an accurate equation for your plane. Now, we just did an example where the plane was determined by 3 points. A plane can also be determined by 2 intersecting lines. If we're not sure whether the lines intersect, then we must first check to find out whether they're parallel, intersecting, or skew, like we did in section 11.5 lines. So we did an example where we checked to see if the planes intersected, and you would have to go through that process if you're not sure. The reason for this is that only 2 lines that intersect at a single point will determine a plane. If you already know that the 2 lines intersect at a single point, then any point on either line will be in the plane, because both of your lines are completely determining the plane. So you could let t equal 0 to easily find a point on the plane. Since both line direction vectors are in the plane, a normal vector to the plane can be determined by the cross product of the 2 direction vectors. So in this practice problem, we want to find the plane determined by the intersecting lines lowercase r of t equals 8 minus 4t, 3 plus t, 2 plus t, and uppercase r of s equals 2 plus 2s, 1 minus s, and 14 plus s. Now in a previous video, we actually showed that these 2 lines do intersect at a point, and we're told here that they're intersecting lines. So we know that we can actually determine the equation of a plane from these 2 lines. So because we know they intersect, any point on either line is in the plane. So if I let t equal 0, I'll have lowercase r of 0 equals the point 8, 3, 2. So the point 832 is in the plane. I'm going to call that x naught, y naught, z naught because those are the letters that I use in my definition for the equation of a plane. And now we need a normal vector. So remember that we want to take the cross product of the two direction vectors of the lines. So my direction vectors come from the numbers attached to the parameter. So in lowercase r of t, I'm going to have v1 equals -4, 1, 1 because I just take the numbers that are attached to t. For the line uppercase r of s, I take the numbers attached to s. So I get v2 equals 2, -1, 1. Now I want their cross product, so I get a normal vector to the plane. So n equals v1 cross v2. I set up my matrix ijk -4, 1, 1, 2, -1, 1. So v1 in the second row, v2 in the third row, and ijk in the first row. So this is equivalent to 2i plus 6j plus 2k, and there's my normal vector to the plane. Now I just need to put everything together. So that's my A, B, and C. And remember the equation for a plane is A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. So I have 2 times x minus 8 plus 6 times y minus 3 plus 2 times z minus 2 equals 0. Remember the point that we found was letting t equal 0, we got the point 832. And so that's where the -8, -3, -2 are coming from in this equation. Now again, to simplify, you distribute and then gather your like terms. So we get 2x plus 6y plus 2z equals 38. So that's how we determine the equation of a plane. Always a normal vector and a point, and then put it into that standard equation.